Good morning to you all. Thank you for joining us today for this session. This is Jagannathrao Mudda from Netflix, working in consolidated logging team. At Netflix, I am building Schema-Aware data streams of user behavior and application performance data that enables analytics and personalization using technologies such as Flink, Spark, Kafka, Hadoop, etc. Prior to Netflix, I have several years of experience in leading software engineering teams and also building large-scale high-performance batch and real-time processing systems in domains such as online advertising, web analytics at Yahoo, data warehousing at Bitiota, data platform at LifeLock, Symantec, and continuous data protection services at BMC Software. I am with my colleague Ramayan Tiwari, and here he is.
Hello everyone, my name is Ramayan. I work alongside Mudda in the data science and engineering organization. I've been working with large-scale distributed systems for a while, primarily in distributed data stores, message queues, and pub/sub systems. Before Netflix, I led data infrastructure team for self-driving cars at Cruise Automation and worked in distributed job scheduling framework at Salesforce.
Thank you, Ramayan, for the introduction. We are here to present a session on schema-aware data streams at Netflix scale. We all have heard of the term 3 V's of big data, which stands for volume, velocity, and variety. These 3 V's represent the challenges of getting insights from big data. The data volume and data velocity are typically handled by building scalable infrastructure. However, addressing data variety has been challenging for most of the technology companies, and it is very critical for the data quality. The 3 V's become even more challenging when an organization experiences high scale in real time. For Netflix, its presence over 190 plus countries with 167 plus million members makes it even more difficult as the user behavior is widely different across different geographies. We support millions of devices with a wide variety of platforms. TVs, mobile, browser, game consoles, and streaming sticks are the most common devices. A quick reference to some of the statistics of 3 V's specific to Netflix. Note that these numbers are limited to user behavior data coming from client devices. Around 400 plus billion events being collected every day, and that translate into petabytes of data per day at rest. This is the volume of one of the largest data streams at Netflix. There are few other data streams having similar volume. In terms of velocity, we receive 350K plus requests per second in real time, and that is the velocity we are handling in our team. These requests are translated into 7 plus million events being processed per second. Finally, the variety. There are 450 plus event types in structured and semi-structured format being sent from millions of client devices. We are able to handle volume and velocity at Netflix with sophisticated auto-scaling infrastructure. However, there are challenges to handle data variety to provide high-quality data insights. Here are some of the challenges of data variety at Netflix. The disparate data from various sources like user behavior and application performance data from client devices, production data from studios, non-members data from partners comes in with different format and structure. Joining such disparate data to get data insights is business critical but challenging. Let us deep dive into data variety challenges, specifically user behavior data and APM data. As mentioned in the previous slide, we have many event types that are coming from millions of client devices with different versions of desktop, mobile, and televisions. Most of the devices are latest and upgradable. However, few are very old and not upgradable. Hence, there are different versions of client software running on these devices and sending different kinds of event data. In addition to this, there are various UI platforms like iOS, TV, Android, web, etc. that produces the event data. The platform teams are independently defining new event types and updating existing event types, creating some inconsistencies in the data stream. Similarly, there are different kinds of consumers of this data. Some are streaming and some are batch consumers who are using different technologies to process this data. When there are so many facets of this data, consistency in interpretation and processing is very critical. If there are no defined processes in place, it might impact the quality of the insights that are derived from this data. Let us look at how data variety, if not handled properly, will impact the data quality. There can be misinterpretation of this data by different consumers, leading to inconsistent metrics and data insights. It might lead to poor recommendations and personalization. There can be inconclusive A/B test results that can indirectly delay decision making or sometimes end up with wrong decisions. It can also increase the turnaround time for feature enhancement and app performance improvement. Ultimately, there can be a decrease in member joy, leading to churn. Few other impacts of this data variety. Most of the time, data producers and consumers are independently working towards their priorities. When a data producer add, update, or deprecate event types, it could break data consumer apps, resulting in bad user experience. How can we handle the data variety issues? First thing is limit producing unstructured data. If not possible, curate the unstructured data as semi-structured or structured data. Secondly, schematize structured or semi-structured event data. Finally, build the schema-aware data streams across the data organization by defining the schema in a centralized schema repository. If a specific event is being passed through multiple streams, the definition of that event type should remain the same unless it is transformed as another derived event or aggregated as another metric. This helps producers and consumers to be in sync with the data format and schema to have a consistent interpretation of the data. Before deep diving on different steps of building schema-aware data streams, let us look at current architecture of the data pipeline that is collecting and transforming user behavior data. When our members are watching Netflix, many user behavior and application performance events are being sent in batches to our ingestion service. The service does decomposition of batch of events to extract one or more events. The event data captures context and also the client-side sessions that are active when an event is triggered. The extracted events are returned to Kafka topic based on the origin of these events like TVUI and non-TVUI. The Apache Flink applications read the data from one of these topics and enrich the data stream with geo and member information. It also projects some of the commonly used attributes from the event. Finally, it writes the enriched data stream to outgoing Kafka topic. There are many consumers of this data stream. One of the major consumers is this another Flink application that performs config-driven transformations and projections of selected fields based on the consumer needs. It generates different outgoing streams for every config and writes to specific Kafka topic. The original enriched data stream is partitioned and stored in the data warehouse for querying and also for further processing by batch consumers. The event data that is flowing in this pipeline is in JSON format. A lot of JSON parsing and processing is happening in this pipeline. Also, similar JSON processing is happening in all the consumer apps of this stream with a lot of compute overhead. We will discuss how are we able to avoid JSON processing and getting compute benefit in upcoming slides. Now let's go over the design phases of building schema-aware data streams. First phase is schematization, where data producers can define schema for different event types. Next phase is schemafication, where event records are generated based on the schema. Third phase is about schema validation of the generated event records. Finally, integration of these components with streaming application to build schema-aware data streams. At the end, define schema for data at rest and implement required UDFs. We will go over design challenges of every phase that we discussed in previous slides, especially the challenges of building schema-aware data streams for user behavior data. Schematization challenges. How to handle ever-growing new event types and updates to existing event types to meet new business use case or product feature requirements. How to define schema for these different event types and notify client apps or server-side streaming apps. A bigger challenge is how to handle evolution of these types. Next, schemafication challenges. Where do you perform the schemafication, client side or server side? If it is done in client side, then how can you push the schema updates to millions of devices running with different client software? If there is any centralized schema registry, how can those millions of devices access the schema registry? If the schemafication is done on server side, then how can we push the schema updates to thousands of servers without service disruption? Schema validation challenges. When to have this schema validation, compile time or runtime? How to handle schema non-compliant records? Next, challenges of building schema-aware data streams. How to define schema for data streams generated by stateless and stateful streaming application. How to handle schema evolution of data streams. How can consumers get access to the schema for every stream? Finally, the challenges of data at rest. Is there any need for defining schema-aware datasets? How to make these datasets cost-effective and still highly performant? For each of these phases, we will go over the different design approaches and reasoning for selecting a specific design approach in detail in upcoming slides. Let us discuss about the design of schematization phase. As we discussed earlier, there are many UI platform teams who are the producers of the user behavior and application performance events. We have introduced a pull request process for adding or updating any event types so that it can be reviewed and approved. When the PR is approved, a CI pipeline will generate the Avro schema for that event type and registers with the centralized schema registry. The schema registration service notifies all the schema clients that are subscribed for getting notification for any schema updates. When a schema client which is part of the streaming application receives a notification, it fetches the latest schema from the registry. The schema client caches the recently used schemas so that any subsequent call to fetch the schema is from the local cache. The schema client is encapsulating and running all these activities in the background so that the application can fetch the latest schema without incurring any additional cost. The next biggest challenge is how to handle schema evolution. There are three types of schema evolutions: backward compatibility, forward compatibility, and full compatibility. The full schema evolution can be considered only when the entire ecosystem is supporting schema evolution. Here the ecosystem means every client app and data streaming app need to support schema evolution, which is a bigger effort and that can be achieved in phases. Hence, we have considered the backward compatibility support for schema evolution. An example of backward compatible schema is if any new mandatory field need to be added in an existing schema, it will be defined as an optional field in the Avro schema for a fixed duration. Once this field is getting generated by every data producer and adopted by every consumer, then it can be marked as mandatory. The same thing is applicable for deprecating mandatory fields. We have online documentation for all these event types based on the TypeScript. It describes these mandatory fields as mandatory. However, Avro schema generator will be defining these fields as optional fields based on a tag in the TypeScript. This facilitates data producer and consumer to make the necessary changes for the new mandatory field and gives some time for rolling out this change. We also have a quality dashboard that gives report on schema violations of UI platforms so that they can prioritize and take care of those issues. These are the techniques that we have used to handle schematization challenges discussed earlier. Let us discuss about design approaches that we consider for schemafication. There are two options for generating event records based on the schema. One was generating on the client side, another one on the server side. We didn't consider client-side schemafication as accessing the schema registry from millions of devices outside the Netflix VIP was very challenging. In case schema registry is not considered, then any updates to schema requires a new application version to be pushed to all the client devices. Hence, we have considered server-side schemafication. The event records are generated based on the latest Avro schema in the Flink application when events are landed in the server side. We call this process as Avrofication, as we are generating Avro records based on the Avro schema. Let us look at the detailed design in the next slide. We discussed current architecture of event processing pipelines earlier. As you heard that the ingestion service receives event data from millions of devices, does decomposition, and finally writes data to Kafka topics. The Flink application that does the enrichment of event data is going to do the verification. The source operator pulls the data from Kafka topic and deserializes the JSON record. The schema client is part of the transformation operator. It gets the schema updates from schema registry and fetches the latest Euro schema asynchronously and copies it into local cache. The Euro record generator uses event factory to generate Euro record based on the JSON event data. The event factory gets the latest schema from schema client, which is backward compatible. It creates and returns an instance of Euro record for every event. This record is further enhanced and serialized using Euro record serializer. If there are any issues like data type mismatch while creating the Euro record, then the original JSON record is returned back. That JSON record also goes through the regular enrichment and finally serialized using JSON record serializer. This is how we are doing the schemafication on server side. The major design challenge for this phase is taken care by schema client, which is getting the schema updates without disrupting the schema. The next phase is schema validation of these event records. Since we are verifying the event records as part of the schemafication, we have evaluated validation support from Euro. Euro has an option of defining Euro specific record, a POSO, for event type. The Euro event factory can create an instance of Euro specific record which will validate the data type of each field. The constructor of Euro specific record can enforce mandatory fields to be passed while creating the object itself. This validation is done at compile time when the record is getting generated. However, it requires building and pushing a new image for every schema updates. Hence, we didn't go with this approach. We have considered generating Euro generic record which has a map of key value pairs to store fields and corresponding values of the record. The schema validation happens at two levels. The type checking is done while creating the instance of Euro generic record. The mandatory fields validation is done while serializing the Euro generic record. The serializer validates the record against Euro schema for any missing mandatory fields. In both these error scenarios, the error message is captured in a separate field in the data stream and corresponding JSON record is returned to a separate Kafka topic. The sequence diagram represents the sequence of verification steps including validation steps. As you discussed in the previous slide, the schema validation happens at two different levels, one at verification and the other one at Euro serialization. From the sequence diagram, we can see that when there is any verification or Euro serialization failure, original JSON record is enriched, serialized using JSON serializer. The JSON record here represents a schema non-compliant record which will be returned to a schema non-compliant Kafka topic. The Euro generic record represents a schema compliant record which will be returned to corresponding schema compliant Kafka topic. This is how the schema validation is done for every event record. The major challenge of segregating the schema compliant and non-compliant records along with capturing the schema errors is taken care in this phase.
Thanks, Mudda. So, what are some of the features that we would like to incorporate into a schema-aware data stream? Well, first and foremost, a stream should support a wide variety of primitive, composite, and custom data types. In our use case, an event is composed of some context details about the action, a snapshot describing the session or state at the time when the event occurred, and finally, a set of attributes to further enrich that particular event. As the events move through our data processing pipeline, Flink applications are further enriching these events with details like geo, member information, A/B test allocation, and many other details that are available only on the server side. Flink application can potentially transform an event into a different shape or form required by different use cases. These changes can only be supported if our data stream features schema evaluation. Finally, many of our stateful streaming jobs perform some form of aggregation on the stream, while others offer a generic config-driven mechanism to apply transformation on the fly. We keep this in mind while designing our data streams. Keeping the noted requirements in mind, we came up with this design. The design in this slide represents a concrete example of various data streams, streaming applications, schema registry, and their interaction with one another. In this case, we have three streaming applications represented by light blue shaded boxes. Each of these applications have the ability to serialize and deserialize Avro records based on the event schema by using our Java library. Each of these applications are constantly listening to events from schema registry to discover new schema or update an existing one. Schema is also cached locally in the Flink application to optimize this interaction. Each of these applications are performing some form of application specific or generic transformation to the incoming events. These outgoing events are then serialized into appropriate Avro records based on the outgoing event schema. By generic transformation, what we mean is some config-driven transformation that can be added or updated on the fly. In this diagram, those configurations are being read from the S3 bucket. As you can see in the first Flink job, the Avro schema is defined and registered only once as the transformations are statically defined. In the second Flink job, transformations are defined via S3 config. Any update to this config will trigger a schema addition or update. The third job is interesting as it is stateful and maintains aggregates on some metric by keeping an active window of the events. The state is stored locally in Avro format using RocksDB. By keeping our state storage in binary format, we achieved major optimization in the state size of this job. So far, we have been discussing schema on data streams, where data lives for a finite amount of time before going to some sort of data warehouse. This is where things get interesting, since the data access pattern of a data warehouse is widely different from that of a data stream. Most of the queries in our use case would greatly benefit from columnar table format like Parquet, as they are only looking at one or more column at a time. Our analysis of access patterns on the data warehouse shows that most of the commonly accessed fields were small fields available as a promoted column, while the raw event were available as a JSON payload. This is where we chose to go with a hybrid approach, where we only applied Avro serialization on the raw events while keeping promoted columns in the native data format. By doing this, we still kept the queries simple, utilized columnar storage for query performance, and also gained storage saving by keeping our largest column in a binary format like Avro. This diagram depicts the actual interaction among data streams, Flink applications, and our data warehouse. The stateless Flink job reads raw events from a Kafka stream, invokes Avro serializer, and applies some application-specific transformation before these events are moved to the next Flink operator, which is responsible for writing these events to our data warehouse. Iceberg in this diagram is Netflix's homegrown table format with native support for schema evaluation. Columns can be added, removed, renamed, or dropped with, with all this support natively built in the system. We have also developed an Iceberg sync for our Flink jobs, which is used in this case to write transformed event in the Parquet data format to our data warehouse. As you can see in the table, ID and event columns are kept in native data format, while the snapshot, which is our biggest column in terms of size, that is kept in Avro binary format. We offer custom Avro extract UDFs to apply the schema on read while querying the table via Presto, Spark, Snowflake, or any other query engine. Now that we have gone through various design phases, I wanted to provide some details on what we have achieved by this initiative. It was a long and tedious journey, finding the owners of each event type, convincing all the partners and stakeholders to onboard with schema categorizing events which don't comply to the current schema, and gradually migrating all those use cases to an Avro schema format. Now we can ask the question, Was this journey worth it? Well, to answer that question, I have listed down some concrete metric on the achievement of this initiative. We now have a well-defined schema for each event type, which helps in guaranteeing that everything flowing through our data streams conforms to the agreed schema definition, and any changes introduced will not break the consumers. Each consumer interprets the events in exactly same way, resulting in great data quality. We segregate non-compliant events in a separate stream where producers can analyze breaking changes in real time. This has a tremendous impact on developer productivity and our velocity. Data in motion is now binary instead of JSON or any other text format. This reduced our compute usage by 30%. 30% at Netflix scale translates to millions of dollars in saving. We now require 40% less storage for data in motion as well as data in rest, thanks for binary storage optimizations that we achieved through Avro. Overall, the cost of our end-to-end ingestion and processing pipeline was reduced by approximately 40%. To sum it up, we reduced cost while increasing data quality, which is a win-win for all the stakeholders involved. In this slide, I want to go over the changes we made to our existing data processing pipeline that my colleague Mudda has introduced earlier. Netflix consumer app is sending log events via HTTP post containing a JSON payload. These requests get routed to one of the instances in the ingestion service. To recap, we used to perform decompaction at this stage. This is where we create individual log events from a compacted batch of events. This process typically creates around 15 log events from one HTTP request. Each of these events translate to one Kafka message. Integrating Avro early in the stages of the pipeline enabled us to perform all data enrichment, transformation, and other event processing tasks in Avro format itself. Since Avro processing is much more efficient compared to JSON, this change freed up a lot of compute power in the Flink application. With more headroom in the Flink app, we moved the decompaction phase of our pipeline from ingestion layer to the Flink application itself. Now that ingestion service is working with compacted events, it leads to smaller CPU and memory footprint. We have also reduced the Kafka message volume between ingestion service and the Kafka cluster by around 15x. Finally, I want to wrap this talk by summarizing the impact this initiative had to the data science and engineering organization. All of our data consumers, whether streaming or batch, are now aware about the schema of any particular data set they are consuming. Any changes to the schema are only rolled out when we can guarantee that it is backward compatible. So no more breaking consumers because of schema changes by producers. The metrics collected through data pipeline are consistent than ever before. Since these metrics power many business critical dashboards, we are getting significantly better business insights and are making better data driven decisions. Since most of this behavioral data is used to train ML model, the data quality improvements are helping us provide better recommendations of shows and serve a more personalized experience to our members. By improving data quality, we are helping Netflix in achieving its core value of increasing member joy. Thank you very much for attending our talk. We will take the questions now.